I'm Greg Shallcross. I'm a technologist at the Jet Propulsion Laboratory in the Chemical Propulsion and Fluid Flight Systems group. And yeah, as mentioned, modeling plume-surface interactions for Continuum and rarefied environments. Next slide. So we all know background plume-surface interactions. It exists for both atmospheric environments, so what you observe on the left, say for like Martian landing, or even on the right for, say, lunar landing, an example from the Apollo 12 landing. The thing is that this leads to a bunch of engineering challenges, which exist for both sort of regimes of flow. This can lead to aerodynamic disturbances during entry, descent, and landing, induced heating, damage from debris, also, say, like surface deformation, and also landing site obscuration during landing procedures. The main focus of this kind of talk is this second to last point, the surface deformation sort of portion. Next slide. So historically, we all are familiar with these particular mechanisms for sort of crater formation and steady-state plume interaction. This includes diffusion-driven flow, diffuse gas eruption, bearing capacity failure, and viscous erosion. These mechanisms all kind of date back to the sort of Viking era. And then recently, there is a sort of subset of the diffuse gas eruption case for this fifth mechanism, which is mainly attributed to pulsated jet for fluidization. The thing is that all these mechanisms are ultimately phenomenological in nature. You can go to the next slide. And when we are describing these sort of phenomenological descriptions of crater formation, effects are going to be fundamentally kind of overlapping with one another. So for example, we can kind of break down each one of these mechanisms into contributions of, say, pressure and shear as a function of our total stress tensor. So all these mechanisms have either some contribution of one, the other, or a combination of both, meaning that ultimately modeling them separately can lead to some significant challenges. So what we could do, kind of just look at some existing modeling methodologies, how we could actually tackle some of these mechanisms or even just all of them together. Next slide. So existing modeling methodologies, we could go all the way to the extremely high fidelity methodologies. So that's shown on the left, such as like CFD, DSMC, like Parvati talked about in the previous presentation, and kind of like multi-phase flow methods. This goes into the Eulerian, or Eulerian-Lagrangian methods. We have something in the middle between experimental focus and fidelity. Those are those kind of like semi-analytical sort of physics-informed approaches. So that's where kind of like Robert's model is with shear-based erosion methods and optical extinction methodologies. And we could go all the way to the right, which is more of the experimental focus side of things, where you actually have functional scaling, where you are directly sort of fitting to experimental data and operating conditions of interest, looking at the variations of different parameters. So go to the next slide. So ultimately, all methods are great, and there's a bunch of different ways you can actually tackle this particular problem, as seen with all the different talks today. But certain methods have certain limitations. Some are computationally expensive. Some are applicable for only certain regimes of validity. And some have high resolution, some have low resolution. Ultimately, the methods have benefits for certain applications of interest. And I'm just going to be focusing more on the sort of non-dimensional analysis scaling side of things. So more of the experimental data-driven kind of approach that has more of these sort of like quick time to solution sort of methodology. Next slide. So to start, we can look at this from a non-dimensional perspective. So using something like traditional Buckingham Pi procedure for extracting relevant terms from a modeling procedure. This first comes with defining a sort of system of interest where we list out the variables associated with our environment and our operating conditions. We can determine some sort of dimensional space where we have available units of interest, such as length, mass, time, etc. We can define independent variables to describe those dimensional spaces. And then the remaining terms are used from a modeling perspective. So using Buckingham Pi, reference, you can go back to your fundamental fluids book for the actual procedure. You can solve for m minus n pi terms, and then you can combine and manipulate pi terms as necessary to get your non-dimensional terms of interest. Next slide. One thing to note is that this is a way to extract terms relevant for your system of interest. It's not a way to derive a model. The model, which I'll talk about on the next slide, is more kind of like informed from, say, a variation of pi terms being described by all other pi terms, and also from the idea that combinations of non-dimensional terms are non-dimensional themselves. So I've just included a few different references for some sort of non-dimensional analysis and dimensional scaling and everything that are kind of relevant to this sort of methodology. Next slide. So here, this is just an example for saying like a length scale variation as a function of all other variations from non-dimensionalization. So here, as we mentioned before, we can describe one particular pi term as a function of all other pi terms. And here we need to make a sort of modeling choice of how to actually describe the variation of those pi terms as a function of others. And here we're just assuming that it's going to be a power law variation of a product of powers of pi terms multiplied by a constant out front. So non-dimensional terms, product lead to a non-dimensional term. And this is typically common in literature. I have a few examples if individuals are interested. And then finally, we could rearrange the expression such that our modeling term of interest, we can multiply through by units in order to get our C out front being a constant. That actually ends up being just sort of like a dimensional sort of variation term. And we ultimately have our model. Next slide. So we could do this exact same procedure for, say, Plume-Surface interactions in crater formation. The example I'm showing here is for depth and width of a crater, where doing the same procedure, we have a product of pi terms. We have some sort of dimensional scale variation where we can convert here. I'm just showing it for time variation to length variation, which shows up in our C prime term. And ultimately, the same procedure can be done for width of the crater. The main difference is that your fitting parameters for your power law variations and also your functional fit out front ends up being variable based upon the experiments that are using to inform said modeling procedure. Next slide. So we can go ahead by using experimental data to try and fit and provide length scale variations for some of these sort of modeling procedures to create a model. So here I'm showing it for depth as a function of time from a few different experimental data sets, one of them including the physics-informed ground test one, and this is for parabolic craters. So left is the experimental data that's using to inform the model, and then right is the output of the modeling data as a function of input parameters. Next. And we can do the same thing for crater width. Width of the crater as a function of time, experimental data is on the left, and the output of the model is on the right. Next slide. And here's just an example of just sort of the non-dimensional collapse for depth of the crater shown on the left and width of the crater shown on the right as a function of non-dimensional time. So one thing to note, is it a perfect model? No, there are going to be length scale variations and errors associated with different experimental runs and stuff. And also, as shown here, we have some experimental sort of like scatter of data for earlier times. This might be attributed to different rates or different regimes of crater formation that really needs to remain to be seen and kind of sort of jumped into a little bit more. Next slide. But one thing I note is that that was for parabolic crater formation. And typically in literature, we have rarefied and sort of continuum crater sort of like formation regimes. Continuum crater regimes are typically associated with parabolic craters, rarefied kind of typically associated with annular craters. This is kind of seen with the formulation of like Robert's model, where you see this donut-shaped crater that ends up forming, which typically has this annular crater shape has typically, like say, like 3 length scale variations. You have a depth, you have an inner width and outer width, while parabolic you would have just say a depth and an outer width. But if you go to the next slide, this isn't necessarily tied to the environments of interest as we typically kind of see in literature, and it might be kind of directly informed by the experiments and evolutions of different behaviors that we might experience during the crater formation process. Next slide. So here I'm just showing an example from PFGT1 from one of the runs, it should be R34MDS, where you actually have a transition from a time variation from an annular crater shape, so showing that wavy W shape in blue, yeah, thank you, to a parabolic shape. So one thing is that you have transition of different regimes where you actually have crater width that will grow in time, depending upon if you're talking about inner crater or outer crater, which will evolve as a function of the granular behavior. Next slide. So crater ultimately forms, you have the shear-driven process, granular material is incompressible, so it kind of shears away. That leads to some sort of like dips and depths for like a donut-shaped crater. This eventually transitions to some sort of like constant depth growth. And next slide. And eventually you get to the point where you reach a threshold and stuff starts to collapse in on itself. And at this point, you actually have all depths start to collapse in, leading to some sort of like more parabolic nature of a crater. So the thing is that you're not necessarily observing a sort of purely rarefied or purely continuum approach. It could be a transition between the two. Next slide. So here's just a quick summary of like what we talked about. I know I kind of rushed through at the end. Ultimately, it's all based upon non-dimensional analysis and kind of showing how we can derive new models for different crater shapes. And I will leave it for there. And the following slides are kind of like the bibliography and background and acknowledgments. So anyway, I'll stop talking.